Good morning. Good evening. Hope everyone's doing well today. My name's Tom Kirk, and we're just going to wait a couple minutes here so folks can join in. So today's webinar, while we wait, it's on the role of HIL in inverter-based resource development and integration. So it's going to be a good one. We have a couple of really great guest speakers. So it's my pleasure to bring to you Dr. Kevin Zhang from Sungrow. He'll be second following my brief introduction. And then we have Xiuchang Bao from Keliang, and he's going to give us an overview of activities in China and where that's going as far as renewable energy and the HIL practices surrounding that. So we're just going to wait another minute or two, and then we'll get this going. While we wait, a couple things. So number one, this will be recorded. You'll have access to this following the webinar. We'll post it. So if you can't make it throughout or you want to share it, no problem. That'll be online. Secondly, we have a Q&A button. It's on your interface. If you have questions at any time for any of the speakers, you can submit the questions using that feature. Some of the questions may be answered in real time by our hosts in the background, or we might save the questions and present them directly to our guest speakers at the end of the webinar. And if we cannot reach those questions during the webinar, we will get back to you afterwards. So it looks like we're getting people joining in, hopefully from around the world. And all right, so what is the structure for today? We're going to go over some brief announcements, an intro by myself, followed by Kevin's presentation, and ending with Xiuchang and the question period. So make sure you hang around for that, because I think we'll have some good ones today. All right, so a lot of you might already know about OPAL-RT's presence at the IEEE PES General Meeting. This year it's in Seattle. Don't forget to register for that. It's more casual than the conference, so you're going to expect some retro video games, some good demos, especially focused on the hot topics at hand. You can find the registration links online at our website or on LinkedIn. Just look out for the promotions. Following that, on the Friday, we actually have another event more focused on learning. So it's the university morning. What you will have offered to you there is the ability, or the opportunity, I should say, to learn about real-time simulation, including some courses that are being offered between 8 a.m. and 12 p.m. Pacific. So you can also register for that, or reach out to us directly if you want more information. We'll be at Seagrey Paris, so if you happen to be there, come say hi. That's in late August. And finally, if you haven't been to one of our RT events, this year's is international. We're going to be in Brazil, we'll be in California, Michigan, and United States. We're having one in the UK, even the Middle East, Japan, South Korea, and India. The dates are all there, but if you're in that area, definitely register, come say hi. This is a free event, so make sure you check it out. We usually get a really good group of speakers out for that. And also, if you're interested in presenting at any of these events, we also have external people presenting. It's not just OPAL-RT people. So definitely keep a lookout for that. Lastly, and this is good because we have more participants joining, we have our Power and Mind magazine, which is really focused on power systems and power conversion in energy. So we actually have two ways you can get this magazine. So you can find it online on our website, but also if you go on LinkedIn, you can actually subscribe to our newsletter. So that newsletter will show up in your feed along with other articles that are published within the magazine. Check it out. We actually surprisingly have like almost 5,000 people signed up for that. So there's a lot of folks reading. And also, if you actually are interested in having an article within that, reach out to us because we're looking for contributors all the time. All right, so enough with the housekeeping, and I'm going to go with my quick intro here. So for those of you that don't know who OPAL-RT is, we're a simulation company. We're out to help innovators. So whether they're in academia, industry, at utilities, it's all about assisting and enhancing projects and product development, research via simulation. Traditionally, it's been more real-time simulation, but I'll explain a bit about what we're doing more in the acceleration domain. And we're really focused also in inverter-based resource problems. So that's aligned with our company mission, which is to bring simulation to everybody. We're based out of Canada, Montreal, Quebec, and we have offices internationally, along with a distribution network of qualified distributors. So if you're ever looking for someone to speak to, you can reach out on our website. We work with a number of different segments. So we work with academia and research laboratories. We work with manufacturers, and we also are lucky to have utilities using our products for their projects. So the renewable energy outlook, and I invite you to visit this article by McKinsey at the bottom. It's quite in depth and has a lot more information than I'll be presenting here, but it's looking positive. So based on 2022 numbers, the projections are shown here. And there's different models being used, but overall, even with the most conservative model, by 2050, we're half of resources on the grid are going to come from renewables. And with the most accelerated model, over 3/4. So that's a huge change in what we're going to see on the grid, a real shift away from synchronous generators to renewable energy. And when we look at what's happening specifically with solar and hydropower, those changes are estimated to show increases between 6 and 13 times of what we have presently. So that's a huge amount of solar power and hydro that's going to get added to grids around the world. Same goes for energy storage. It's expected to quintuple between not now in 2050, but now in 2030. So in the context of inverter-based resources, this is a huge increase in the amount of power that can be supplied by those resources onto grids internationally. And of course, certain countries have even more penetration than others. So this has a lot of challenges associated to it. What are those challenges? So on the right, there's a graph, and basically this is from NERC, a US reliability organization. And what you're seeing here is the impact of an event on the grid where solar generation is disconnected. So you can see that, and in the context of this event, it wasn't even a grid that was weak. There was substantial inertia in that grid, and it still had this substantial impact on the excuse me, on the frequency. So every year, there's more and more reports of events such as this. So we're seeing that with the increase in those resources, it's only gonna have more and more impacts. So how IBRs are used as grid forming devices, their ride-through capability, the configuration of that is crucial. There's going to be challenges associated to the frequency and volt-var regulation, protection schemes. So because of where they are placed in the circuits, old protection schemes are not necessarily going to be applicable to the new grid. So those techniques are being revised. There's some really good articles already on that topic. How are we going to restore systems? So black starts with these low inertia systems. And then finally, islanding and cybersecurity. So in the context of a microgrid, improving reliability during blackouts for distribution. These are all things that are being worked on constantly. And of course, cybersecurity, you have many devices connected more than ever before in this smart grid. That's a huge concern because you could have potential cyber attacks that could have a massive impact on the grid by attacking these resources. Real-time simulation. So what do we mean by real-time simulation, and what are the main applications? So in this graph or this figure, this is for a microgrid application, but it can apply also to transmission and other applications. The whole idea behind this is you can simulate the grid, you can connect different controllers or protection devices. So whether it's a primary control device that say controls a power electronics converter, or a protection device that is taking signals at a substation or elsewhere, or if you have a secondary controller, so that could be a microgrid controller, an energy management system, an ADMS, and then finally tertiary control functions, so higher level. The idea is we can replicate the grid at different levels and connect those devices to test them. And usually that's at a signal level, a low voltage signal level and digital communication protocol level. So using standard communication protocols. And then on the bottom, we have what we call power hardware in the loop. And what that does is we take signals from the simulation and we convert them from digital or low voltage signals, and we generate power. So we actually will push power through power converters, other devices to test them at the rated power. More focused on hardware in the loop. So looking again at the microgrid example, we can actually simulate not just the different generation devices and loads and the buses and network in the simulation. We can actually simulate devices themselves. So if you look at the bottom left, you'll see a darker green square. It says FPGA. So we can simulate power converters at very high frequencies on the FPGA. And that allows us to really connect primary power electronics control at a high frequency. So, you know, we can simulate these things at rates of a megahertz. And then on the CPU, you can have systems more in the 50 kilohertz range. So it's still electromagnetic transient simulation, but within that, you can also simulate protection relays. You can emulate controllers. So you can do all sorts of stuff to build a very detailed analogy of the real scenario. So we're going to see a bit more on that after from our presenters. And one aspect that is important is smart inverters. So how do we simulate a smart inverter, especially when there's so many on a grid? We want to use that in the context of a real-time simulation. So we actually worked with Resources or Natural Resources Canada, the CanMet office, and we developed a smart inverter library together, which runs on both our main platforms. It's based on IEEE standard 1547, and you can use that to effectively put a simulation of the controls and protection of the smart inverters that reflects or represents grid forming or grid supporting inverters based on that standard. There's a webinar that we did previously on this, so we can point you in that direction if you want to learn more. Finally, I mentioned power hardening loop. It's a huge asset for a lot of different activities. So the one thing is that you're not just testing at a low voltage signal level, you're actually testing devices under power, under rated power. So some of the applications that you can test or perform are type testing. You can have interaction studies with different devices. You can validate vendor models or your own models. You can test protections systems at power. And on the right, I think this is a really good example from Hydro-Quebec that was presented during a previous webinar. They're showing how using P-HIL, they can actually characterize the performance of a solar inverter in a weak and a strong grid setting. So one of the fundamental things here is that when they did these tests, there was actually a closed loop interaction. So it wasn't just a signal being amplified and sent via the power amplifier with no feedback. There is a feedback loop that goes to a simulator. This can be quite complex, and it's something that we have worked hard on to understand, and we even made our own amplifier that operates at a higher rate. So this is a huge topic, and I invite anyone interested to look it up on our website. There's a really detailed section with a lot of good content also from users at our Power Hardening Loop page. And lastly, we have gone down the rabbit hole of large-scale grid simulation. And I say rabbit hole because this is really hard stuff to simulate. We're not just looking at simulating large power systems. We're looking to also simulate the IBR plants and controllers. So you can see on the table on the right, these are some of the numbers of the different elements of the simulation that we were simulating for an Australian network. There's a whole paper on this if you're interested, but it turns out that this is actually a huge challenge, not just because of the grid size, but also because of the controller code that we're implementing within the simulations. So if you're a vendor out there and you want to work with us on these sorts of problems and optimize your code, we would love that, because we can really do great things in this area together. And there's such a growing need for this large scale simulation that we think this is the future. So yeah, we're looking forward to working on these problems going forward. So before we start with our presenter, we have a quick poll, which should be popping up any second. So the first poll is, what is your main objective in attending this webinar? This is just so we can understand what to bring to you down the road. And then which, there's a typo, excuse us, which of the following IBR applications are you most focused on? You can just select one and submit it. So we'll give you a few seconds to complete that. Okay. I guess I have to submit the poll as well. Let's try it. Okay, so I think we can move on. So I don't think you can see these results, but the two top answers for the first one were to learn about the latest trends in simulation and industry, and to learn about industry practices. And everyone in the second question was asking more about the control side and grid integration. So thank you so much for sharing. So next up, we have Dr. Kevin Zhang from Sungrow. So I'm gonna just introduce him very quickly and he'll share his screen. So as manager of Sungrow's Power Electronics Research Center, Dr. Zhang leads various R&D projects in the areas of renewable power conversion system modeling and simulation, grid integration control, grid forming technologies, and artificial intelligence-aided power electronic system design. He has been with Sungrow for 7 years. He obtained his PhD from the University of New South Wales in Australia. It's a pleasure to have Dr. Zhang connected, especially at the late hour, as he's located in China. So no further ado, I'm going to stop sharing my screen, and Dr. Zhang, it's all yours.
Okay, thank you. Thanks, Thomas, for the introduction. Okay, hello, everyone. It's gonna be good morning, good afternoon, and good evening. Okay, this is Kevin here. So I'm from Sungrow. Today, I'm very happy that OPAL-RT can provide this such opportunity to let me share some experience that we are using hardware in the loop simulation and real-time simulation for our power converter and energy storage system applications. And I just saw the poll, the results of the poll. A lot of you are interested in converter control HIL simulation. So I'm happy that I'm gonna share some ideas and experience from our daily work. Without further ado, First, I'm gonna introduce our understanding of hardware in the loop simulation. Then I will show you what Sungrow use real-time simulation and HIL simulation, show you the HIL simulation lab we had here. And then we're gonna share some simulation cases. So first, please let me introduce a little bit about Sungrow. For this, you might haven't heard about Sungrow. Sungrow was established in 1997, and the headquarters is located in Hefei, China. And at the beginning, we are a PV inverter manufacturer. Now, our two significant business, including PV inverters and energy storage. So now we have, globally, we have 3 manufacturing bases, one in headquarters Hefei, China, and one in Thailand, and another in India. And we have 6 R&D centers in Shanghai, in Hefei, Shanghai, Nanjing, Shenzhen, and Munich, and Amsterdam. We have 20 plus international subsidiaries, just showing here from North America and Europe, and also Australia and Northeast Asia. And our network covers like 170 plus countries. So this is from the revenue chart, you can see the market is expanding very quick. Last year, our revenue reaches 10 billion US dollars. And the total installation of PV inverters for last year comes to 130 gigawatts, which is 100 times than the year 2012. Here's our PV inverter products. We do have modular inverters and string inverters, also have a residential inverter. And it's being ranked the #1 in global PV inverter shipment. And here's our energy storage system. So we cover utility scale energy storage and business scale storage system, and also residential storage. So last year, our shipment of storage system reaches 10.5 gigawatt hour. And besides PV inverters and energy storage system, we also have business in renewable energy plants development, wind power converter, and inverter and charger for electrical vehicles. And also we have hydrogen equipment manufacturing as well. So actually across all the business, the HIL simulation is used all across all the business departments. And you may wonder why it is so popular that HIL simulation is in Sungrow. So in the rest of the presentation, I will share with you why this is so popular. So then let me explain from our perspective what hardware in the loop simulation is. So a lot of colleagues that haven't heard of real-time simulation or hardware in the loop simulation, they come to me and ask what it is. So I will always use a metaphor to help them to better understanding what it is. So let's consider a racing game and a power system simulation. So in the this graph shows a real-world racing. So not every of us has a chance to go on a track or to afford a Ferrari or Lamborghini in our real life. So, but we still want to enjoy excitement of racing cars. So what are we gonna do? We can play video games, right? Like Need for Speed. So, but for the video game, you just use the console controller and watch the screen. You cannot feel the motion and acceleration, right? Then here comes a VR. So that's kind of bridge that connects video game to the real world racing. So it's give you a more immersive way to enjoy the racing. Like you can feel the actual acceleration and braking. So compared to our real power system simulation, so real world racing equals to real power system, right? And video games just like digital simulation, like Simulink or Piscat. And hardware in the loop simulation is the VR of power system simulation. So the basic I think the base for hardware in the loop simulation is the real-time simulation. You have to achieve real-time to enable hardware in the loop simulation. So what is a real-time simulation? From this clock here, we can see it's running fast than real-world clock. And the second one is slower than the real-world. Only the third one is synchronized with the real-world clock. So we call the third one real-time simulation. Okay, once we can achieve real-time simulation, actually we have a new pathway of simulations that we can connect. I consider real-time simulation as a pathway that connects digital world and to our real world. We can build PV modules, batteries, converter, IGBTs, or grid and loads in real-time simulator, and then connect our hardware controllers to the system, like inverter or PCS controller, BMS, EMS, and PPC controller, and etc. So as Thomas mentioned that there's a power hardware in the loop simulation. The one I'm talking about here today is controller hardware in the loop simulation. So in Sungrow, we mostly use controller hardware in the loop simulation, and the rest of this presentation is all about controller hardware in the simulation, in the loop simulation as well. So I even asked ChatGPT what's the benefits of HIL. So ChatGPT gave me 8 bullet points. I'm not gonna go to detail of each one, but I pick up 3 most significant benefits of HIL provide us from our daily work perspective. The first is enhanced testing and validation. So the realistic testing environment HIL provides can help us to detect software issues in an early time. So that is help our R&D teams to accelerate their software development for a significant amount of time. And the next one is safe testing of edge cases. So we can test extreme hazardous scenarios. For example, for all kind of grid contingencies, like voltage fluctuation, frequency fluctuation, and phase jump. So normally this cannot perform in a real power plant. Otherwise, you may jeopardize the safety of the network and get a penalty from the grid. The last but not least is time and cost efficiency. So it accelerates development cycles by a large margin. So it reduces need for physical prototypes. And when the physical prototype is ready, so 90% of the software test has already been done on HIL. Another reason besides R&D needs, R&D requirement of the HIL is actually the marketing and the solution team also requires HIL simulation. That is because in a lot of areas and countries, they require every grid integration projects to provide HIL simulations. One example is Australian AEMO. And I think that's the first grid operator that requests HIL simulation for their grid connection application, probably around the year 2016. And then now the US ERCOT and California ISO is also require the benchmarking of the pure digital power simulation to benchmark with HIL tests. And also the HIL test already being included in IEEE standards as well. So, and recently, as I learned that in Middle East, especially Saudi Arabia, from the year of 2023, all new grid connection projects has to provide HIL simulation results and all the network connection studies with HIL. Okay, now I'm gonna have introduce a brief introduction of our HIL simulation lab in Sungrow. So actually, we have more than 20 OPAL-RT simulators. Most of them are OP 5000 and 5700. Due to the FPG capability, so we can simulate very fast switching converter devices up to 60K to 100K. What we use hardware in HIL for testing, we mainly use that for two types of tests. The first is individual converter controller test. So we have PV converters or energy storage converters or wind power converters, and also EV drive units. So we build these models like PV and battery and wind turbine in our real-time simulator, and we connect their converter controller to the OPAL-RT system via I/O and DI and I/O and the communications. So then we can run the whole system in a closed loop. That's the first type of simulation we do normally. And the second is power plant controller HIL simulation. So in this case, we can build like microgrids or large scale power plants in the OPAL-RT simulation system. And then we connect BMS, EMS, or PVC real controller to the system to test their control algorithms. And another powerful tool is thanks to the comprehensive Python API that OPAL-RT provides, RT Lab provides actually. So we can use Python, pure Python scripts or professional automatic test case managed systems to build automatic HIL automatic test bench test platform. So we can do automatic data collection, analyze, and plot the figure. And also we can automatically generate the test reports. So without human on site. So it's very convenient. It's like we just press the start button, and then at the end of the day, then we come back to the next day. All the tests has been done, like hundreds of tests has already been done, and also the report is generated. And another part of this is it can generate tons of data that we can use for our AI model training. So it's another advantage that if you put together the automation and RT Lab, it will generate, it will largely increase the efficiency of testing. So here I'm gonna share some simulation cases that we've done previously. The first one is the simplest, just one inverter controller connect to one real-time simulator to run all kind of grid connection tests. So we built a big grid HIL test platform, so we can test both grid forming and grid following control strategies. We can test their extreme low SCR condition, like we push them to the limit to see what's the lowest SCR it can the inverter can work. And also we can perform consecutive high voltage read through and low voltage read through tests, and also frequency response tests. And we developed an inverter impedance sky test too to generate the border plot of our inverters. Here's another usage that we use HIL for model validation, because HIL just takes the actual control hardware from our actual product. So it represents the controller's actual performance in the real product. So we normally use this as a benchmarking for other digital simulation models. Here's a comparison of another digital model with our HIL simulation. Okay, another case is power plant controller HIL test. So in this case, so based on the last only inverter test case, we here included another PCS or EMS. So it connect via IEC 104 or Goose communication protocols directly to our inverter controller. And then we measure the voltage and current at the POC and send to a smart meter, and the smart meter will connect to PPC controller. Then the PPC generates control algorithms based on the voltage and the current measured at the POC and send a dispatch signal to our inverter controller. So in this case, we can mimic a whole power plant. Instead of building a real power plant to test the PVC, we can run almost all the tests of the PVC's function via this HIL test platform. Here's another case that we use two simulators run in synchronization. So in this graph on the right-hand side is our best system hardware in the loop test system. So this is mainly to test our BMS. We have our BMS controllers connect to our cell models in the real-time simulator. And the other side is the PCS controller HIL test platform. So we can use fiber optics to connect these two devices, like these two real-time simulator, and run the whole system simultaneously. So in this case, we can simulate like thousands of battery cells. We together with our BMU, our local controller, and the power plant controller, together with our PCS. Here is the actual project we run in our HIL system. So that's a project. That's a that's a power plant black start project. It's one project in the US. So before we went to the set, we run the whole process on our HIL simulation, and we identified some of the control algorithms issues before went to the site and fixed at home. And when the team goes to the site, when the team goes on site, so it only takes days to have the system running smoothly. So that's the whole process we've been run on our HIL simulation platform. So upper side is the current, and the lower side is the voltage. So the first part is multiple PCS startup in synchronization. You can see the voltage is built up gradually, and then we come to the main transformer excitation, and you can see the surged current that's due to the saturation of the transformer, and then some resistive load cutting. Then the other current surge is motor cutting, and here the steam turbine just start up, and our PCS, the voltage here, the PCS just changed from grid forming mode to grid following mode. Okay, that's pretty much all for my presentation today, and thank you for everyone's attention. Thanks. Back to you, Thomas.
Oh, thank you so much, Kevin. That was amazing. It's great to have you on. I'm just gonna share my screen again. So I think I have the right one up. So just a reminder, we have been receiving some questions, but if you haven't, or if you have any questions, I should say, that you'd like to ask, now's the time, because the sooner you put them in, the higher you'll be on the list. And next up, we're actually having our second poll. So you'll see it pop up on your screen shortly. All right. So first question is, which of the following test benches would you be most interested in seeing offered? So the reason we ask this is because we're always working on test benches. For example, we have a microgrid test bench, but if there's something you'd like us to work on or release, we'd like to know more. And then the second question is more for us to understand what you want to see as an audience. What topic would you like to see covered in a future webinar? So more about advanced simulation techniques, more about product functionality, case studies from industry, or more on the trends in the renewable energy segment. It'd be great to have that feedback so we can best meet your needs. Note the second question is multiple choice. You can select more than one. So I'm not sure the results are going to pop up again for this one. So while we're waiting on that, I am going to introduce our next speaker. So it's my pleasure to have Xiuchang Bao, a technical manager of the Integrated Energy Division of Keliang. He's in Shanghai. So Xiuchang has long been engaged in renewable energy, integrated energy, and hydrogen energy system modeling and hardware-in-the-loop simulation and test. He's performed in-depth research in renewable energy and hydrogen energy system modeling and simulation, along with system planning and optimization operation. So, and this is our last speaker, but stick around for the question period. And if you can't, make sure you catch the recording. So I'm going to stop sharing my screen, and it's all yours, Xiuchang.
Okay. Thank you, Thomas. And I will share my screen. Yeah. Okay. Hi everyone. Yeah, this is Xiuchang Bao, and yeah, I'm from Shanghai Keliang company, and I'm very it's been a pleasure, yeah, being invited by OPAL-RT to attend this webinar, and today I will share with you the subject, the renewable energy simulation technology, supporting the construction and operation of new type power systems in China. As you can see, my presentation is divided into three parts. Firstly, I want to give you some background of China's new type power systems. And then I will move on to the new requirements of simulation technology for new type power system. And finally, I will introduce some typical use cases. Okay, regarding the, the background, sorry. In September 2020, the policy of carbon peaking and carbon neutrality was issued by Chinese government to fight the climate crisis. As we all know, the electrical power system is the primary area for energy conservation and carbon reduction. So to achieve the double carbon goal, the strategy of building the renewable dominated new type of power systems was proposed by our president for the first time in 2021. And there are two typical features of the new type power systems. High proportion of new renewable energy and high proportion of power electronics. In this slide, I would like to review some numbers of the installed power capacity and power generation last year. As you can see, by the end of 2023, the total installed power generation capacity in China is about 2.92 billion kilowatts. The non-fossil energy installed power generation capacity is about 1.57 billion kilowatts. It exists that of thermal power unit for the first time, and the preparation is also exist 50% of the total installed power generation. And also the last year, the renewable energy power generation is about 1,100 billion kilowatts hour. Is also about 12% of the total power generation. And we also can see the tendency in these two figures about the annual carbon dioxide emissions and also the total power generation and the non-fossil energy power generation. The proportion of the non-fossil energy power generation by the end of 2060. Yeah. So with the construction of China's new type power systems, different types of energy resources are integrated into the power grid. And also the new energy storage is also widely used to supporting the construction of the new power type power systems. And the electrification is becoming more and more popular in the whole society. Electric energy is increasingly used in industry, for example, in industry and transportation, and also the community. And this slide, I want us to review the application of the new energy storage. Now, the new energy storage system is a very important spot to the construction of new type power systems. And we can see in this pie chart, by the end of 2023, the total installed capacity of new energy storage has reached 30% of the total energy storage systems. And among all of the new types of energy storage, the proportion of lithium-ion batteries is the highest, almost reach 60%. And then we're talking about the hydrogen energy. In 2022, the Chinese government announced the medium and the long-term plan for the development of the hydrogen energy industry. And the hydrogen energy has also been returned to the energy law of the Chinese Republic of China this year. So it will play a very important role in the future energy system. And we can see that the hydrogen electrical coupling is the most important ways to realize the large scale and the long-term storage of the electric energy. Yeah. Along with the rapid development of the new type of power systems, the problems and the challenges also rises for the safety and the stability of power grid operation. The traditional generator-dominated power system is transforming to converter-dominated power system. For connecting the new energy and also the the battery energy system to the power grid, the state grid and also the National Energy Administration have issued many technical standards and technical specifications to ensure the safe and stable operation of the power grid. To achieve this, one of the main tools or ways is using the hardware in the loop simulation and the test platform. For her green hydrogen industry, we all know that these years the industry is in the time of high speed development, but the whole industry technical or engineering level is still in the early stage. How to improve the skill levels of, for example, the coordinative planning and integrated design and flexible control, and also the energy management for green electricity and green hydrogen and green chemical industry is the current research hotspot and also the pain points right now. So this also needs the supporting of the simulation technology. Okay, in the previous chapter, we reviewed some background. And next, I will move on to the new requirements of the simulation technology. Okay, the first requirement of simulation technology, especially for the hardware in the loop test, I think is accurate simulation of the high frequency electronic. The high frequency power electronics technology is now widely used in the area such as the energy route for a hybrid AC-DC microgrid, also for the solid state transform, and also for the power resources like a UPS. And the frequency of the switching frequency exceeds 100 kilohertz. The second requirement is for the energy storage system. We know that especially for the new energy storage based on the lithium and iron batteries, the the BMS and the PCS, for example, the grid forming type, and also the EMS, they are all needed to simulate and test during the R&D and also before the application. For EMS simulation and test, we got two test scenarios here. For example, the first one is a multi-level. I mean the multi-level controllers like BMS, PCS, and EMS. And also we have the multi-time scale for hybrid energy storage system. We got different types of the new energy storage. The batteries, the supercapacitor, and the compressed air, and so on. And the last requirement we talking about here is about that for the integrated energy systems. The simulation technology will be very helpful to improve the skills levels for the system planning, design, construction, and operation. And we also have two application scenarios here. The first one is the integration of different types of resources like wind, solar, hydro, and so on. So we're talking about energy base. This is very popular in recent years in China. We can use the energy base to fulfill or to realize the multi-energy complementary coordination. And the second scenario is the integration of generation, grid, load, and storage. It is a heterogeneous energy storage system. We have different also the energy type, the heating, electricity, the gas. And for this system, we focus on the research. The research focus on the multi-cycle dynamic response and also the cooperative control, and also the optimized design and energy management. Okay, finally, I will introduce some typical use cases in China. The first case is about a grid-forming hybrid inverter hardware in the loop test with the 5th generation of EHS solver. In comparison to the 4th generation of EHS solver, the 5th generation allows the accurate simulation for high-frequency electronic systems, such as the resonant converters, for example, using the LLC topologies. And the supporting switching frequency is about 200 kilohertz. And we have successfully tested all-in-one hybrid inverter in our lab. And the inverter has different electronics topologies, like the boost and the buck the boost, and also the LLC, and Herrick type inverter. And the switching frequency in this case is 100 kilohertz. The second case is about an EMS HIL test for large-scale energy storage station. And in this case, different types of controllers are connected to the real-time simulator, like the PCS controllers and coordinated controllers and the EMS for the whole energy storage station. And in this case, under one collector line, we have 15 PCS, and we connected. We mod and simulate the whole 15 converters, and also with the transform and also with the collect line in 4 scale. This means that we connected the 15 PCS controllers to the simulator real-time simulation platform, and the circuit part of the converters are simulated in the capsule FPGAs, and the number of the real-time simulator depends on the number of the controllers connected to the system, and also depends on the I/O terminals used for all the PCS controllers. And based on the PCS hardware in the loop, we can connect a real coordinated controller to the system. The coordinated controller communicates with the 15 PCS controllers via communication protocol, and he will send different commands to the PCS controllers under the different test conditions. And for the other collect lines, for example, we got other 15 or 20 collect lines. These PCS controllers and the circuits and also the grid are all virtual. And we can, the original control algorithm for each PCS controllers from the manufacturers, yeah, we can, they are encapsulated as a dynamic link library into the Simulink model. And finally, we can connect a real EMS energy management system of the energy storage station to the whole system, and we can fully test the functionalities of the EMS. Okay, the third use case is also a controller hardware in the loop application about power electronic device. The difference is the power electronic devices here, such as power supply equipment for electrolyzer or a fuel cell inverter. Yeah, these devices are used in the new field of energy system. So this case is still about the main application of the EHS toolbox in power electronics system. Yeah, for example, this is about the power supply equipment for electrolyzer, the DC bus and the converter circuit, and also the electrolyzer is simulated in the real-time simulator. And the real controller, for example, the DC for DC-DC is used a real controller, and they communicated with each other. It communicated each other with I/O terminals, I/O interfaces. Sorry. And the last case is also an EMS HIL test, but for a new type integrated energy system, contains wind, solar, storage, hydrogen, and fuel cell. And the EMS here in this system, the main functionalities is to, for example, to make sure the maximize consumption of new energy, and also to fulfill the multi-energy complementary coordinate, and also the safety and the stability of the system under the different conditions. For example, the off-grid, and also the fault conditions. So based on the HIL test platform, we can fully test the functionalities and the performance of the EMS here. Okay, this is the end of my share, and thank you all for the listening and attention. Okay.
All right. Thank you so much, Xiuchang. So we have reached the end of the presentations. We're a little over, but that's fine. So we're just looking forward to some questions here. Last chance if you need to get some in. No need to share the screen for this. We'll just do it live. So here's a good question for Kevin. So this one comes in and it's a question about requirements. So the question reads, there are different requirements that are coming from transmission operators, TOs. Does Sungrow provide the complete inverter model for additional HIL that TOs want to perform? Or only a PSCAD model? So Kevin.
Yep.
Good
question, Diego. As you said, that's correct. There's different TO has different requirements. Like some of them just requires a digital model, like in PSCAD or any other Dixeling or any other pure digital model. But to validate their model, to validate the digital model, they require a comparison between HIL test results and the digital model result. So you have to do a benchmarking test. So you have to list a comprehensive test cases and overlay the waveforms that's running with HIL and also the digital simulation model. So make sure these two align together so that can be to assure that your digital model is accurate to represent your actual products. So some TOs requires you to provide also the HIL model and also provide a inverter controller together with the model to them. So they can run tests by themselves to validate your digital model. Yep, that's the answer to the question. Thank you.
Okay, thank you. Thank you very much. Another question that came in was someone asked, they would like to know more about co-simulation of two OPAL-RT systems. Where can we find more information? So it's very dependent on the application. So there's a few different methods to do that. We ask that if you do have such a need that you reach out directly to us so we can best answer your question. We also, I should mention, can co-simulate with other real-time systems. So if you do have other systems in your lab or other simulators, we can do that as well. Another question we have from the audience is how, and this one's for Dr. Zhang as well, how do you assign and organize your 20 simulators? That is a lot of simulators. Are they for different products? Yeah, if you could give a bit of perspective on how that works, that'd be appreciated.
Yep. Actually, all the simulators are purchased at a different time, and we are not running all them together in one lab. So we are not using, we are not connecting them all together, or just use their use the computation power for like grade level simulation. We don't do that. So actually, we these 20 simulators are distributed to like 7 or 8 different places. So each different business unit have their own R&D labs, and they have their own digital simulators. So yes, so it's used for different products. Yep.
Okay, that's great. Thank you for answering that. So I'm just looking at the question list. We're really late on time here. So unfortunately, since we're over, we're gonna have to end that here, but we do have the questions from other attendees recorded, and we'll make sure to reach out following the webinar. Again, I'd like to thank our speakers for joining us so late in China, and our audience. Thanks so much. Have a great day, everyone, and look forward to seeing you at our events or in person whenever we get the chance. Take care and have a great day or evening.
Thank you.
Thank you.
Thank you.
Bye.
Bye, everyone. Yeah, bye.